All right, let's get started. Lecture 4, you made it through the first week. So you all submitted homework 2.1. How was that? Hopefully it wasn't too bad.
Easy peasy.
It wasn't bad, but it did. I will say it did throw me for a while since the supports weren't on the end.
Yeah.
So it took me longer than it should have to kind of think through and get around that issue. I almost emailed you before I figured it out.
Yeah, you can sum moments at the support, but you have to account for the loads everywhere, including the load on the other side. So, yeah, no, that's understandable. So I think that was probably, the only super tricky part. Am I right?
Yeah, once I got past that, it was just plug and chug with what we did in the notes.
Yeah.
It was just trying to make sure I was thinking through that without screwing it up. Like the distances were what threw me, because I got the point and I got the load easily. Yeah. But just making sure that I had the right distance from the support.
Or how you resolve those distributed loads and whatnot. Yeah. No, I can understand that. The homework today, there aren't any good problems in the textbook that explore just this concept. So, for example, there will be problems with inclined loads or rollers, but they also have concentrated moments, or they have something else, and those are concepts for another day. So these two problems are actually going to be custom. One of them I took from this textbook, but then I tweaked it a bit, and then the other one I actually got from another book, and use that one. So, but yeah, today's lecture is primarily focused on taking loads and inclining them, or taking rollers and inclining them. But let's handle some logistics. So attendance grades, they're posted, they're up to date on Blackboard, and I think now that we've gotten through the first week, I don't think we're going to have anybody adding the class late, and hopefully nobody, or not a lot of people dropping it. So I can go ahead and I think be a little bit more regular in getting the attendance grades posted. Homework 1 is graded. If you go to Blackboard, you will see a folder called Older Homework Solutions. And so if you open that folder, there's a post for Homework 1, and it shows the homework assignment and the solution. And so I typically try and ensure that for every assignment, there's a solution that's posted along with it. That's valuable, and I think it'll be helpful throughout the course. Later on, when we start using Mastan, you'll actually be able to independently, come up with these yourself. So it's pretty cool. Probably at some point later in the semester, I'm actually going to have a homework assignment where I just have you all install Mastan and actually show that that everything works and whatnot. But that's later on down the road. We're going to keep on trucking with the homework pattern. So you're going to have homework 2.2 assigned today, due Wednesday, and then we'll keep on going from there. So everybody good? All right. So let's get into inclined loads and roller land. I think that if there's any one theme with this course as opposed to statics and mechanics and materials, it is that in here, the intention is to take the tools that we developed in statics and mechanics and make the tools easier, but simplify the tools to handle problems that are a little bit more complicated. And already we're taking these problems and we're ratcheting them up a bit from what we did in statics. We're going to take that and do that even more today. And what I want to do is I want to include the possibility that loads are not, perpendicular. It would help if I plugged in the receiver for this. I don't think that quite goes to the 7 mistakes per semester counter. So again, though, it's a corrupt system because I'm the one who tracks the mistakes. That was a joke, not very funny. Okay, so from the previous lecture, our goal through the last lecture, this one, and the next two is all about support reactions. And really, as structural engineers, these are the primary ones that we deal with. There are some, what I would call more advanced analysis techniques where you might try and account for rotational stiffness and things like that. But other than that, primarily this is what you're dealing with. And those cases are really once in a blue moon situation. So really the three primary boundary conditions we're dealing with are pin supports, roller supports, and fixed supports. We haven't yet dealt with fixed supports definitively. We'll start that on Wednesday. So really we've been dealing with simple supports. Remember, simple supports are hinges or pins and rollers. These are the ones that do not resist moment. And by the way, there is a good chance I will interchange when I'm talking about supports, the term hinge support and pin support. From a support condition standpoint, they mean the same thing. So if I interchange that a bit, my apologies. Okay, for dealing with concentrated loads, those are pretty straightforward. For dealing with distributed loads, the idea is that we idealize them into an equivalent concentrated force. The magnitude of that force is equal to essentially the area under the load diagram. So in the case of uniformly distributed loads, we just take the magnitude of the load multiplied by the length. So that's the force. And then we place that at the centroid, which for a rectangle is halfway over. For a linearly distributed load or a triangular load, we take the area of that triangle, which is 1/2 base times height, that's where we get that. And then the centroid of a triangle is 1/3 of the way from the big end. And that's what we dealt with last time. So everybody good with that conceptually? Okay. All right. So inclined loading is a possibility that we need to consider. Note that loads can be inclined as well. We tend to define loads and their inclination using one of two concepts, either an angle or a slope ratio. And I think that probably mathematicians or those of you who are more inclined to think about this from a math perspective are probably more comfortable with angles. So for example, you're probably more comfortable right now with something like this. So if I have some force that is applied at some angle theta from the horizontal, I can convert that into x and y components. And the x component would be the magnitude of that force times the cosine of the angle, and then the vertical component would be the magnitude of the force times the sine of that angle. Now, I want to, this little yellow box here, I do want to make sure that this is crystal clear. Just be careful when using the angle. Like, these formulas work, but these formulas assume that the angle is referenced from the horizontal axis. So for some reason, I said theta was like this angle right here, this angle right here, then these formulas wouldn't work. You'd have to swap the sine and cosine terms. Just, don't think, well, Dr. Mike put it in the slides, that's the formula. Just, you make sure that you're being a little more global in your analysis. Okay? So this is, I think, where the mathematician comes in. But I would argue that most engineers are speccing out inclines, at least in terms of structures, on a rise over run basis. So for example, according to the American Disabilities Act, okay, there is a certain slope that you have to spec out for handicap ramp, accessible ramps and whatnot. So for example, the walkway out here in the building. So if you walk out the door to the front of the building, there are stairs that take you out to the sidewalk, which will let you access 3rd Avenue. Or if you need the accessible ramp, you go down the ramp. There is a slope ratio that ramp has to go along. And you will very rarely hear somebody say that it is such and such an angle or whatnot. Usually they'll say something like it's a 1 in 12. Or for every 12 foot over, you go 1 foot down. So it is very common as engineers to express things in terms of slope ratios. So a common slope ratio is what you're going to see in this coming example. We have a load at a 3 to 4 slope ratio, right? Okay. Now, personally, I am of the opinion that I tend to try and make my math as easy as possible. I want to do as few calculations as possible so that I can go home at the end of the day and not worry about it. So there's 2 ways of handling this. The first is I have to be a mathematician, so I have to take the inverse tangent of the horizontal and vertical to get the angle, and then take that angle and take the sine and cosine of that angle to get the x and y components. Or I could just use the slope ratio directly and recognize that the cosine is adjacent over hypotenuse. The sine is opposite over hypotenuse. And so if I know the hypotenuse, I could just use those slope ratios directly, and it's a lot faster and a lot easier than going through and doing the former process, finding the angle with an inverse tangent and taking the sine and cosine. I think also by doing it that way, you tend to introduce more potential numerical errors. So in the case of the next example that we're going to do, The load is at a 3-4 slope ratio. So if it's 3 and 4, what's the hypotenuse? 5. So one component is 3/5, one component is 4/5, right? But if you use an inverse tangent, the angle is like 57 degrees, and then you take the sine of that, and so instead of getting 3/5 and 4/5, you get this decimal that trails out, and you introduce error when there really isn't any error present in the problem. Again, keep it simple whenever you can. Okay, so I tend to prefer using the slope ratios whenever possible. We're going to use that a lot in truss analysis and things like that later. It's going to make our life a lot easier. So far, so good? All right, let's go through an example. So here's an example where we're taking the concepts and we're ratcheting them up just a little bit, okay? So first off, notice how I am including concentrated loads and distributed loads. So we're dealing with stuff that we dealt with last time, but now I'm taking it and I'm just adding a little more, okay? So we've got a concentrated load, but it is at an incline. It has a magnitude of 20 kips, and it is at a 3-to-4 slope ratio. I'll give you all a sec to get all the particulars and whatnot written down before we get into it. Okay, so while you all are drawing this out, let's see. So the first thing I'm going to do is I'm going to identify my support reactions. So we have a vertical here and a vertical here. We'll call this, oh, sorry, I'm getting backwards. BY and AY. Now, we have here a horizontal reaction. I'm going to do something, okay? We've been assuming that horizontal reactions up until now are acting to the right. I'm going to go ahead and do that. Now I'm just going to blanketly tell you, that's wrong. It's not acting to the right. It's acting to the left. I'm just telling you. But I'm going to do that, okay? Because I want you to get comfortable with the possibility that you make an assumption and it's wrong. Because there are going to be problems where that's going to happen. And it doesn't matter how good of an analyst you are. So I'm purposefully making an incorrect assumption here so that you can see how the math bears out. Okay? So I want you to see that. Okay. Now, what else can we handle? All right, what about this distributed load? Let's handle this like we did before. So we have a distributed load. I'm going to collapse that into a single point load. What's the magnitude of that point load going to be? 14 kips. And then from this support A, we'll say that this is 5 feet. Okay. Now, for the now let's deal with the incline load. Okay. Now for the incline load, we have a 3-4, but we already recognize that if we have a 3-to-4 slope ratio, the hypotenuse is 5. Okay. So what I'm going to do is this. I don't like dealing with incline loads, just like I don't like dealing directly with distributed loads when I'm computing reactions. I want to take this and resolve it into its components. Okay. Now this load is acting this way, which is sort of a down and to the right sense. So I'm going to take this and I'm going to split it into a horizontal and vertical component. Okay? Now, this is just a SOHCAHTOA problem, right? So the cosine is adjacent over hypotenuse. The sine is opposite over hypotenuse. So the hypotenuse is on the bottom, right? Okay? So it's really easy to do this. Okay? So for this vertical component, it's going to be 20 kips times something over 5. And this horizontal component is 20 kips times something over 5. The hypotenuse goes on the bottom because, again, sine opposite over hypotenuse, cosine adjacent over hypotenuse. What goes on the top? It's really easy. Just follow the slope ratio. See how the smaller number is on the horizontal axis? Smaller numbers on the horizontal axis, put the smaller number here. Bigger numbers on the vertical axis, put the bigger number there. That's it. That's all there is to it. So this is going to be 20 times 0.8, that's 16 kips, and this is 12 kips. Does that make sense? Is that okay?
Yeah.
Shouldn't be too bad, right? Okay. All right. Now, let's start off with summing moments at A. Let's sum moments at A, and let's see what we get. All right. So let's just take care of this one step at a time. Do I need to consider AX? No. Do I need to consider AY? No. The 14 kips, do I consider that? On the left or right side of the table? It belongs on the left. And the moment arm is 5 feet. So 14 kips times 5 feet. All right. Okay, now this inclined load. Do I deal with the horizontal component? No. So just so that everybody is aware, I'm drawing these beams with some depth associated with it. But for the sake of our discussion, we can assume that that beam is just a line. So if that load is applied right here on that line, that horizontal component goes directly through A. So the horizontal component we don't need to worry about. But the vertical component we do. The vertical component is generating moment. It belongs on the left side of the table. That's 16 kips. At a moment arm of what? How far is that from A?
18 feet.
18 feet. And then we have BY resisting it at a moment arm of 24 feet. So, save myself a little bit of space there. Okay. So 14 times 5, that's 70. 16 times 18, I think that's 228? 288? 88. So 288 and 70 is 358. Did I do that right?
Yeah.
Foot kips, again, that's my little shorthand for that, equals BY times 24. And so BY is going to be positive. I don't think I'm that good. We'll say 2 decimal places. What are we getting for that?
14.92.
14.92. Do I have a second?
Yeah.
All right, so 14.92 kips. And so what that means is, let's just be clear, I achieved a positive answer, and so when my initial assumption was vertical, was vertical acting upwards, not vertical, that's acting upwards. This is upwards. This positive answer means that my assumption is correct. And so that's going to be a correct assumption. And again, we are going to have problems throughout our class where there's no real way of making a gut assumption. You're just going to have to pick something. And so it's okay that if you make assumptions and they're incorrect. That's okay. It's easy to deal with it. Okay, so what I'm going to do is now I'm going to go ahead and deal with the sum of forces in the y direction. Now that I have BY, I can go ahead and solve for AY. Let's go ahead and do that. So let me scooch this down a little bit. I think that's good. So we'll sum forces in the y direction over here. Thoughts on the table? Think we're good? Is it bad? Okay, all right. So we have AY going up, We have BY going up, but we know what that is. It's 14.92 kips. And then going down, 14 kips, 16 kips. So, scooch down a little bit. So AY plus 14.92 kips is 30. And so AY is positive, was that 15.08?
Yeah.
I did that right? And there we go. Sound good? Now we got one more to deal with. Let's deal with the sum of forces in the x direction. Okay, and so I want everybody to pay attention to this one. This one's kind of important. Okay, so first off, is AX 0? No, it's not, because there's a horizontal component to that inclined load. So this is the first, I guess, instinct I want you to kind of shove aside. Like in the last homework assignment, the horizontal component was 0. We just didn't even think about it. That's not the case here. So I don't want you to get into the habit of, it's just 0. Actually look at it. Actually assess it. Okay? So we're going to draw a similar table. And what I'll do is I'll say everything going to the left and everything going to the right. I'll actually go through and do the assessment. Now, what I have here, though, is something that hasn't happened yet. Okay? So I have AX to the right, and I have 12 kips to the right. Do I have anything going to the left? No. Something's not right there. Like that should give, something's wrong. I mean, everything up until now, we've had stuff on one side and something to balance it out. We don't have that over here. This means our assumption's wrong, right? That's what this means. It's okay. It's just, I want you, if this happens during a homework assignment or an exam, I don't want you to see this and panic. Like, it's okay. Just follow it through. If you've done your math correctly, it will bear itself out. So over here on the left, I have 0 equals, on the right, AX plus 12 kips. So if I solve for AX, what I'm doing is I'm subtracting, and I'm getting that AX is negative 12 kips. What that means is, it doesn't mean I need to develop significant emotional distress. All it means is I assumed in my free body diagram that AX was acting to the right. That assumption was wrong. And it just means that AX is 12 kips to the left. That's all it means. Okay? So, no real concern to deal with. So, what's my answer? My answer is AX is 12 kips to the left. This is 15.08 up.
So you don't want a negative answer, you bring
No, not for the end, because that's a good question. So typically no, because the negative, I'm trying to word this correctly, it doesn't really mean anything. The negative is just tied to the assumptions that we made, right? So let's put it this way, okay? I assumed that the reaction was acting to the right, and I got a negative answer. You might go, no, I can see that it's acting to the left, and when you draw the arrow to the left, you're going to get a positive answer, right? But regardless if I get a negative answer and you get a positive answer, what we are both going to get is 12 kips to the left. And so that's really the answer. So does that make sense? So that's why when I sort of circle my answer, I don't really have signs. I just have, remember back to statics. What is a vector? A magnitude and a direction, right? So I have a magnitude and a direction. Magnitude, direction. That's a really good question. Yes?
So, I can understand the whole negative thing, but I'm just right short. So if the 12 was on the left side of the table, like where we have our AX and stuff,
Mhm.
you just get 12 kids equals AX without the negative, so therefore we still have the arrow going to the left.
Yes, because the only way that would work is if I had drawn this the other way.
So, like with our answer, we kind of have negative 12 kids with the arrow to the right, but that also means
12 kids. Yes, that's exactly what it means. Because it was funny, I actually just had this lecture this morning in statics, and I said that if you have a vector, right, and you multiply it by a negative number, what you're doing is you're doubling the magnitude and flipping the direction, right? It goes back to from that basic definition. So, in fact, everything here, how are we splitting this up into x and y components? It's that tip to tail thing, right? Remember, we have a vector like this, so it's that plus that, right? So we go down, then over, and that's the resultant. Same concept. This is good stuff. I really like this. Now, I actually do want to make a side comment about the software analysis we're going to do later. The way that most structural analysis packages work, including Mastan, right, is when you input your modeling criteria and you hit go, it analyzes everything. It'll tell you every reaction, every truss force member, whole 9 yards, right? And so it'll basically spit out a table with every support reaction, right? So let's say you have a structure that's got 15 different supports. Like this one only has 2. It's not that unheard of that real world structures have oodles and noodles of them. It will spit out the answer in one big table. And what it will do, like let's say for your vertical reactions, is it'll just say positive reactions act upward and negative reactions act downward. But it's doing that because it's a software program and it's got to find a means of expressing that to you as the user and the analyst in an easy fashion. But for the purposes of us as analysts in this class, what I am interested in is that you understand the context. Everybody, regardless how you do this problem, should get what's in this box, right? That here's the magnitude, that's the direction. Here's the magnitude, here's the direction. Here's the magnitude, here's the direction. For example, I could have assumed all the vertical reactions acted downwards, and I'd have gotten negative answers, but that would be the same for everybody. Does that make sense? This is really good stuff. I really like these types of conversations because I want to make sure that everybody's on the same page. Especially when we start dealing with internal hinges, because we are going to get reactions going all sorts of different directions for those. It's good stuff. Everybody good? Okay. Now I'm going to take this concept regarding inclined loads, and I'm going to complicate it a bit. Because I tend to do that. I'm just kidding. Not really. Okay. So now what I want to do is instead of dealing with inclined loads, I want to deal with inclined supports. Now, to be clear, the only support condition where this is going to matter is for inclined rollers. Because for pinned conditions, for pinned and fixed conditions, you have an independent X value and an independent Y value, and they're not related. So it doesn't matter whether a pinned support or a fixed support is inclined or whatever orientation it is, it doesn't matter, okay? Now, what's going to happen, though, is whenever you spec out an inclined support, what you're doing is you're specking out the inclination of the ground. But what's happening with the actual reaction is, well, let's just say you got to pay attention to the details. Let me go back to the example that I mentioned with the ADA accessible ramp here outside the building, right? So the ramp is, I don't know, something like this, and the support conditions, or the ramp is inclined at a 1 to 12, right? So if I'm standing on the ramp, the reaction is something like this, right? Okay? Notice how the ramp is at 1 to 12. The reaction is going to be at 12 to 1. The slope ratios are going to flip, right? Now, if you're wondering, how did I get flipped? Like, how did I do that? How do I know that by flipping the slope ratios, I have a reaction that's at straight 90 degrees? Comes from this. Remember in algebra, right? If you're graphing a line and you want to know the slope of a perpendicular line, you flip the slope, right? So if this, let's say this purple line, this magenta line has a slope of, I don't know, 3, then this line has a slope of 1/3. I mean, changing signs and whatnot, but signs aside, y'all remember that? So we're doing the same thing here. So like as an example, and what I drew here on the board is pretty much the same thing here, it's just a little bit different context. So let's say I have a roller, and the roller is inclined at a 5:12 slope ratio, okay? So like a 3, 4, 5, the hypotenuse of a 5:12 triangle, 5 squared plus 12 squared equals 13 squared. So that's another one of those special triangles that we'll deal with. So like 3, 4, 5s, 5, 12, 13s, 8, 15, and 17, those are some common Pythagorean triples and whatnot. Now, notice what I've done here for the reactions is I've taken this reaction and I've split it into x and y components. But look what's going on here. See how the 12 is on the horizontal here? Over here, the 12 is on the vertical. Notice how the 5 is on the vertical? Here, the 5 is on the horizontal. Because the reaction is perpendicular to the ground. So the slope ratio is flipped. Does that make sense? So I want to make sure that everybody's understanding that, okay? That's really kind of important. I don't want to just sort of throw that at you because like I'm going to have an example problem here in a second where we actually do this and it's like, whoa, wait, what are you doing, Dr. Mike? Now I want you to understand. So far so good? Okay. All right. Let's do a problem. And I decided to be difficult and throw an angle here, just to make sure that we have exposure to both angles and slope ratios. Okay, so I have a beam that only has a triangular load on it. That's all I have on it. But I have a pin support and I have a roller support at an inclination of 20 degrees from the horizontal. And we need to compute the support reactions. Okay, so I'll show you how to do that and then how we should express it in the end. Because we're going to get two values here, but they're related. And really all I care about is the magnitude of that perpendicular reaction. So let's take a look at this. See, hold on. So this is example 4. Just look at example 7. Look at this craziness we're going to be dealing with. It's not that bad. We just take it one step at a time. Okay. So let's start off with that distributed load. Let's see what we can do with that. So I'm going to take that and collapse that into a single point load. What's the magnitude of that point load going to be? 36 times 4 over 2, so 36 times 2. 36 times 2 is 72?
72.
72 kip. So we've got a 72 kip reaction there. And then that is 12 feet, right?
12 feet per meg.
12 feet per meg, there we go. And again, if there's anything about my handwriting that isn't clear, let me know. I will take it personally, but then I will fix it. That was again a joke. All right. Now, let's deal with this triangle over here. Now, just to make sure it's clear, I want to do a little bit of trig off to the side. Do a little bit of trig off to the side. Let's say this is 20 degrees, okay? And just for the sake of the trig component of it, what I'm going to do is I'm going to say that this has a hypotenuse of 1. So trig tells me that if I have a hypotenuse of 1, that the length of this is the cosine, the length of this is the sine, right? So what is the cosine of 20 degrees? And let's do it in like 3 decimal places, just to make sure we're being specific.
0.940.
And this one is the sine, and this is what?
0.342.
0.342. Do I have seconds on that? Okay. Now, what I'm going to have here is I'm going to have a reaction. And instead of calling it By or Bx, I'm just going to say that I'm going to have a reaction here called RB. Okay? And what I'm going to do is I'm going to split that into x and y components. And notice the way that I'm drawing them. The way that I'm drawing them is not really an assumption. The assumption came from assuming that the reaction is going like this. If the reaction is going up and to the left, then the components are up and to the left, right? I either draw them up and to the left or down and to the right, okay? And that will be very important later when we start looking at trusses, because we're going to have oodles and oodles of joint analyses, and we will have to be very cognizant of the direction that we draw our components. Now, in terms of the magnitude of these components, what I'm going to do is I'm going to say, if RB is the hypotenuse, let me ask you about the horizontal. How much is the horizontal? If this is RB, how much is this? Say it again.
RB times.
Which one?
What's it?
Well, now remember, we're doing this. This is the roller, so remember we flip it. Here's the horizontal here, but when we flip, that's going to go vertical. This is going to be 0.342 RB. Because what's happening is basically what we've got over here is we've got a triangle that looks like that, right? This is RB, so the horizontal is going to be 342 RB, and the vertical is going to be 0.940 RB. So this is going to be 0.940 RB. Because think, this 20-degree inclination, the ground's not really tilted all that much, right? So most of the reaction is going to be vertical as opposed to the horizontal. It'd be different if the ground was at like a 60-degree incline. Then it's like up like this, so most of the reaction is going to be horizontal, not vertical. Does that make sense? Does that make sense? It takes a little getting used to, I know. So far, so good? Okay, so what we're doing is we're just taking the horizontal component, putting it at the vertical component, putting it horizontal, where we flip that out. Now, I think what I can do now is I can look at this structure and I go, you know what, I think we can use a little bit of common sense and say that AY is going to act upward, and AX, I'm going to be smart about it and say that AX is acting to the left. Because I look at the free body diagram, the only force I have that's horizontal is this going to the right, so that's got to go to the left.
You drew it to the right.
Wait, no, that's what I meant. I'm sorry. I meant this is going that way, so this is going this way. Yeah, going to the left. Going to the right. Man, I'm getting all sorts of mixed up.
You know, not that left, the other left.
The other left, yeah. That's another thing. It's like I'm pointing it like this way or this way. So I've got like the Vanna White Weathercaster syndrome going on. So because I'm inverted sometimes from you all, so it'll be all right. Okay. So now that we've got, like, to me the hardest part is actually this part, taking the reactions and drawing the free body diagram. Once you've got the free body diagram, the rest of this is kind of a cakewalk, because I'm going to handle this the same way I've been handling a lot of the previous problems. I'm going to sum moments at A, and I mean, we could sum moments at A or at B, wouldn't really matter. I would, to be honest, I wouldn't really sum moments anywhere else. And to be clear, there's nothing theoretically that says you can't do that. I can sum moments right here if I want to, and I'll get the right answer. The bean doesn't care where I sum moments. The answer is the answer. That doesn't mean that there aren't ways to do this to make this easier upon me as the analyst. You could sum moments at B or at A, and it would result in the same amount of computations. Personally, I'm kind of like a guy that wants to start at the left and work my way over, so that's why I sum moments at A. But and I did mean the left that time. So we're going to sum moments at A. Okay? So we don't have to deal with AX. We don't have to deal with AY. We do have this 72 kips times 12 feet, which is going to be on this side of the table. Okay? Now for the reaction, the only thing that we have to deal with is not the horizontal component, but the vertical component. Because again, I'm drawing it down here, but really it's acting at this point, just as these are acting here, so that horizontal component goes directly through A. I do have 0.940 RB acting like this. So 0.940 RB times a moment arm of 36 feet. And that's it. That's really all there is to it. So what I'll get is let's see, 72 times 12, that's 720, 144, 864.
Yes, sir.
Equals RB times 0.940, 36 feet. So therefore, RB is 864 divided by these two quantities. I'm getting something like 25.53.
Yeah.
Okay. So plus 25.53 kips equals 25.53 kips. Now what's the direction? What were we doing? You're going like this, because what we solved for was RB, not the vertical component, but RB. And RB is kind of going like that. So what I would do is say about like that, because that's the direction, right? The direction is in that vertical component, that inclined component, not the vertical component. So now I've got RB. Now what I can do is handle the sum of verticals and the sum of horizontals independently and get AX and AY. So, yes?
Okay, so if that is just RB, why did we go ahead and account for the vertical component?
What do you mean?
So why did we go ahead and plug in the 0.94 if we're solving for RB like that?
Okay.
Because if we're going to break it down further into components, wouldn't that?
Well, so here's what we did. So we drew our free body. Let's take care of the free body diagram first, right? Yeah. So over here we have an AY and an AX that are independent of one another. Here we have RB, right? And so this vertical and horizontal component is just me resolving RB into its independent components. So before I did the math, are you in agreement with the free body diagram? Okay. So, all right. So if you're with me on that, then when we sum moments at A, all I'm doing is just taking each component and accounting for it. I could throw the horizontal component here if I wanted, right? But it would have a moment arm of 0. It would be going right through A. You see what I'm saying? The vertical component is the only thing that's generating moment. So this is just the sum of all the components in the entire structure that's generating moment in A, and there's only one unknown, and it happens to be RB. Does that make sense? Now I'm not done accounting for both the vertical and the horizontal components. I'm going to do that here in a second. I'm just not there yet.
Okay, I just wanted to make sure that that wasn't already broken down into the components of RB, because I didn't want to do that on the homework and then not have forces accounted for.
No, you won't, because this vertical component is this much of RB. So when you solve for RB, you are getting this, right? So if you wanted, you could take that RB, multiply it by 0.94 and get the vertical component. But that doesn't, you can do that if you want, but really interested in is just what is that RB. Does that answer your question?
Yeah.
Maybe give me a little bit more when we finish it. I think you'll see what I mean.
Okay.
So just bear with me. Okay. So far, so good? All right. So now what we're going to do is we're going to sum forces in the y direction. Now going downward, the only force that I have is 72 kips. But going upwards, I have AY, and I have 0.940 RB. Okay, that's the part that's going upward. So what I'm going to do is I'm going to say, okay, AY plus 0.940 RB is 72 kips. And I'm going to plug and chug. And you should actually get some nice round figures on this. Oh, sorry. If you carry out all your decimals. So, it should actually come out to a nice round figure. If I take 72 and I subtract this, what do I get?
48.
48. Do I have a second on that? All right. Why is it coming out in such a nice, pretty figure? The reason it's coming out in such a nice, pretty figure is because 72 kips is the only load that's on the structure, right? And it is a triangular load put a third of the way from that support. So the way the vertical components ended up working out is that vertical component is 2/3 of this, that vertical component is 1/3 of this. Now, we are very indirectly at this point introducing a concept we're going to deal with later, which is called influence lines. But those patterns, there are some very, very powerful observations we can glean from patterns like that. It's a little premature to talk about that today, but when we get into handling moving loads, those patterns are going to be really powerful, because what we're going to start to ask is not what the reaction is under this set of loads or that set of loads, but instead, what's the reaction under any load, anywhere, and those patterns are going to be really, really important. But I digress. Okay, so that's AY. Now if we sum forces in the X direction, all right, so I have AX on this side. I'm getting it right this time. And I have 0.342 on this side. So this one's probably not going to be as pretty. So 0.342 RB is AX, 0.342, and that one was 25.53 kips, is AX. So what does AX end up being? This one's probably not going to be all that pretty.
8.73.
Do I have a second on that? Yeah. So kips, which is 8.73 kips, acting this way. So to summarize, what we're interested in is the unique independent reactions, and I've got AX is 8.73 kips acting this way, AY is 48 kips acting up, and then RB is 25.53 kips that way. And again, whenever you're dealing with just an incline, so with the previous example with an incline load, just deal with it like you would normally deal with it, sines and cosines or your slope ratios. Just with reactions, you're flipping those ratios. You're taking the horizontal and putting it with the vertical putting it with the horizontal, because of this. Because when you have a line and you rotate it 90 degrees, the slope ratio flips. Because the reaction is perpendicular to the ground. Any questions? All right, I'm going to pull up the code in case everybody or somebody missed it. Other than that, that's all I got. I will see you all on Wednesday.